In the previous lecture, we discussed the representation of orbital angular momentum, L, right? In this one, we will talk about the general matrix representation of the total angular momentum, that is with J is your total angular momentum, and it's the sum of your orbital angular momentum plus the intrinsic spin of the electron. So that's S, right? And the components of J, this thing, are simply Jx, Jy, and Jz. Now, just like the Lx, Ly, and Lz operators, these Jx operator, Jy, and Jz operator, they satisfy the commutation relation that is given with Jx, Jy commutator is equal to iota h bar Jz, right? And likewise for the rest of the components, right? Now, since we have this J squared is equal to Jx squared plus Jy squared plus Jz squared, it commutes with each component the simultaneous eigenfunctions, then the psi jm of J squared, right? Psi jm of J squared operator, and one component, you could say, for example, with Jz, right? You can find these simultaneous eigenfunctions using the relation J squared acting on psi jm, and it gives you h bar J times J plus 1, and it returns you back the same eigenfunctions Jm, right? And likewise, if you have Jz on psi Jm, it gives you h bar times the m quantum number, and it gives you back your psi Jm, right? So it's the similar equations for L that we had, right? So for the orbital angular momentum, we also had L squared was acting on psi Lm in that case, and it would give you h bar times L into L plus 1 and your eigen functions back, right? Those were actually psi Lm, right? So it's the same kind of expressions. Now note that psi Jm is normalized to unity, and it satisfies the orthonormality relation that is in the bracket notation psi j prime m prime inner product with psi jm. It should give you it gives you this delta j j prime times delta m prime, right? So that is, if your j and j prime and m prime are equal, then this thing gives you 1, and if they're not equal, then it gives you 0. That means that they're orthonormal, these eigenfunctions, right? If it gives you positive 1. Now Jz is represented by a diagonal matrix with elements that are we can write these elements of a matrix like psi j prime m prime, and for which matrix we need its elements, say Jz, so we'll put Jz in between, and then we would have psi jm, right? Now if you look at this, what does this thing should give you, right? Well, you see, this Jz would act on this thing first, and from this expression, we know what that is. It is simply h bar m, or let me just write it like this, right? H bar m, and it gives you back your psi jm, right? And over here we have psi j prime m prime, right? But now this h bar and m, they are just constants, so they would not act on this wave function, and that means that we can just throw them outside. So if we do that, we have m h bar and psi j prime m prime psi j m. And from here, if you look at this orthonormality relation, this thing is equal to m h bar and delta j j prime and delta m m prime, right? So what is this thing? This thing is psi j prime m prime and jz on psi jm, right? So this is then your matrix elements of the jz operator. Now in the matrix representation, psi jm are in fact your column vectors, right? Now the eigenvalues of jz and j squared, they are real, and these values can be determined using the following relations. We will introduce first j plus, these ladder operators, right? So j plus is j x plus iota jy. So these are you could think of these as your L, right? When you're writing these expressions, the expressions are same, just the thing is that we are now talking about the total angular momentum with J. And we have for ladder operator J minus, we have Jx minus iota Jy, right? And then the immediate properties of these operators, they are that if you were to take this commutator jz and j plus minus, right? So if you were to take it with j plus or j minus, the values you would get are plus minus h bar and the operator j plus minus, right? And if I were to take this j squared, right, the commutator of j squared and j plus minus, this commutator vanishes, right? So that means they share the same eigenfunctions. Now other relations that j plus and j minus satisfy, they are let me write those down. They are j squared operator, that is equal to j minus times j plus plus jz squared plus h bar jz, right? And this thing can be then written as j plus j minus plus j z squared and minus h bar jz, right? These are actually two different representations, and we could write them in general as j squared is equal to j minus in fact, yeah, j minus plus, right? If you note over here, we switched the positions of these operators, right? And that's why we had this negative sign over here and we had positive over here. So we could write in general this thing, therefore j squared, as j minus plus times j plus minus plus j squared, jz squared, right, and plus minus h bar jz. So I wrote this general expression using these two equations, right? Now consider the relation that we have for j squared, which is equal to jx plus iota jy times jx. Actually, let's write minus over here and let's write plus over here, iota j y, right? If you take the product of these two, right, and add it to jz plus h bar jz, right, and this thing would give you j squared, right? All we did was we opened these two as j minus and j plus, right? Okay, so well, this thing then in general we could write it as jx squared plus jy squared plus iota. All I'm doing is multiplying these two, right? So we would have plus iota times iota h bar jz plus h bar jz plus jz squared, right? Okay, now with all of these relations between j squared, jz, j plus and j minus, we can construct the eigenvalues of jz and j squared, right? That's why we were looking for all of these relations between these operators. Now suppose you have this equation jz acting on psi jm, which gives you m h bar psi jm, right? Now what we wish to show that that this m over here, it is either an integer or an odd multiple of 1 by 2. Well, so to do that, let's consider the following operation, that is jz and j plus on psi jm, right? So it's j plus will act first and then jz. So well, this thing is equal to using the above relations that we wrote, jz j plus minus j plus jz plus j plus jz, right? So we have just done this mathematical trick of adding and subtracting the same thing, and this would act on jm, psi jm, right? And what this gives you is the commutator of jz. Look at this thing, right? It gives you the commutator of jz and j plus, right? And this times this function psi jm, and then plus this thing that we added, j plus jz operator on psi jm, right? Now if you look at this equation, well, we can write this thing as h bar j plus, right? So all we are doing is we are acting this on these eigenfunctions psi jm. So we would get h bar j plus plus j plus h bar m and all of this, from this we could factor out psi jm, right? Now this thing is that well, yeah, now this thing is that jz is now acting on j plus psi jm, right? And this thing is equal to, we could factor out h bar from this expression over here, and we would get h bar times, well, we could also factor out j plus acting on psi jm, and inside we would have m plus 1 on j plus psi jm, right? Now what does this mean, right? Well, this implies that j plus psi jm is an eigenfunction of jz operator, and it corresponds to the eigenvalue, that is this one, h bar m plus 1. So what does this mean? Well, that is that j plus on psi jm is simply equal to psi j m plus 1, right? So if you take psi jm and act it on with j plus, it gives you back psi j m plus 1. So it adds one integer to your value of m quantum number. Well, we could see what would happen if I would apply j plus once more, and well, if I do that, so I would have j plus on j plus psi jm, right? So all I'm doing is adding this j plus again on it. So we would have j plus acting on psi, if you see that this thing from this over here is psi j m plus 1. Now I have to do the same operation on this, right? So I'll look at this equation, right? And I'll write psi j m plus 1, right? So we had m plus 1, and we would add plus 1 to it, and what's that? That's simply psi j m plus 2, right? And so you could keep going on and acting with j plus, and well, you would see there would be a restriction on this, and we would see that very quickly. And well, in this similar manner how we did for j plus, we could write for j minus, or you could do this as yourself as an exercise, but we could write it as j minus acting on psi jm would be equal to psi j, and this would take away take away 1 from your quantum number, so m minus 1. And likewise, if I were to act with j minus again on this whole thing, right, in this similar manner, it would give me m minus 2, right? So thus we have found a scheme for generating a sequence of eigenfunctions of jz from a single eigenfunction, that was this psi j m, with successive value of m in the square differing by unity, right? So well, we could then write this sequence as well, we could have it coming from and we would have some j m minus 2, we would have psi j m minus 1 and psi j m, right? And then we could keep going with psi j m plus 1, psi j m plus 2, right? And we could keep going, right? Now, well, we might use this equation to I might refer to this equation, right? So I'll just label it as some equation gamma, right? Now we know that since this commutator of j squared and jz is 0, right, it vanishes, then what that means is that these two operators, they have common eigenfunctions. So they share the same eigenfunctions if this commutator is 0, right? So, well, we would say that let some psi jm be a common eigenfunction with an eigenvalue h bar k whole squared. So let me write that down as j squared psi jm is equal to h bar squared k squared. K is your well, wave vector, right? And h bar k is your momentum. So the squared of that times it gives you back psi j m. Now let's operate on this equation, right? On this equation with the operator j plus. So let's do that. J plus on j squared psi jm is equal to well, again, these are just constants and we could throw them out, so you would have h bar squared k squared outside, and then j plus would act on psi jm, right? And if I do this thing is the same as if I were to say that I operate first with j plus on psi jm, right? And then I operate it with psi, I operate on it with j squared, right? So you see, that means that we could switch these two operators, right? So, well, this equality asserts that j plus psi jm, right? Or let me write it down, that j plus psi jm is equal to psi j m plus 1, right? This thing is also an eigenfunction of j squared. So also an eigenfunction of j squared operator, right? Corresponding to the eigenvalue. So the eigenvalue is, well, what is it? If you look at this equation, it is h bar k whole squared, correct? So it follows that the sequence of eigenfunctions of jz found previously, right? This sequence, this gamma, right? This one, this equation gamma that we have, right? These are all the eigenfunctions of j squared corresponding to the eigenvalue that is this h bar k whole squared, right? Now let's talk about the expectation value, right? So the expectation value of j squared, and that is, well, we write expectation value like this of j squared, which is actually just h bar squared k squared, because expectation value is like the average value that you would get for your operator if you measure it, and it's the eigenvalue of that operator, right? So, well, but then this thing should be equal to, because we know what j squared is, it should be equal to the expectation value of jx squared plus the expectation value of jy squared plus the expectation value of jz squared, right? But we know that, again, from the eigenvalue equation of jz, we know that the expectation value of jz squared would be m h bar squared, because we know the eigenvalue of jz, and that's mh bar. So if we square it, it would be the square of mh bar. And so then we can write, well, the expectation value of j squared, right, as equal to, well, it's h bar k squared, right? So h bar squared k squared is equal to, well, jx squared, right, plus jy squared plus, now the expectation value of jz, we know all that already, so that's mh bar whole squared, right? Now, what does this equation imply? If you look at it, if you examine this equation, if you stop and think about it, it tells you that this h bar squared k squared should be greater than or equal to m h bar whole squared, right? But, well, you can just see that you could just divide both sides with h bar, right? Or the h bar just goes away, and this implies that your wave vector squared should be greater than equal to m squared. So that's the quantum number m. Well, for the possible values of m in the sequence that was given in this equation gamma, right, it falls between positive k and negative k. So if m max, let's say we have some m maximum, right, is some maximum value that m can assume for a given angular momentum h bar k, then we would have, if I take j plus and act it on psi j m max, right, so the maximum value that m can assume, well, then it would just vanish, right? It would just give me 0. And likewise, we could have some m minimum, so some minimum value that m can have for a given angular momentum h bar k. Then if I take j minus and act it on j psi j m minimum, that would also vanish, right? So this means that if you have reached some maximum value of the m quantum number, you cannot raise its angular momentum, right? So it would just vanish. And likewise for the minimum value of m. Now, from this relation that we had, that is j squared is equal to j minus j plus plus jz squared plus h bar jz, right? Well, from this relation, let's take this jz squared, let's take j squared and operate on j psi j m maximum, right? What should that give you? Let's see. Well, this thing, because we know the eigenvalue of j squared, right, it's h bar squared k squared on psi j m max, right? But from this relation, what would that be? Well, first we would have j minus, first we would have j plus acting on this thing, but we already know what that is from this thing that we just talked about, these two equations actually. If j plus acts on some psi that has maximum value of m, it would vanish, and then j minus would act on it, so that would just also give you 0, right? And so what that means is then this thing acting on psi j m max would give us 0, right? Well, then we have plus jz squared acting on psi jm. So, well, we know the jz squared expectation value is simply m squared h bar squared, right? And so if jz squared acts on psi jm max, well, that should give you m max h bar and psi jm max. So the same eigenfunction back, right? And well, then we have this thing, right? So we already have a h bar, so h bar, and then jz acts on psi jm max, and that would give you h bar m. So h bar becomes squared now because we already had this one h bar over here, and then we would have m max and psi j m max, right? Well, what can we do from here is that this thing which was equal to, this thing is equal to h bar squared k squared psi j m max, it would be equal to h bar squared, right? Well, I'm just factoring out some terms from this. So we could factor out h bar squared, right? And we could also factor out m max. So we could factor out one m max at least, right? And h bar squared, actually we could factor out h bar squared, correct? And we would have inside then m max plus 1, and we would have this eigenfunction j m max. Now there is, all of these are constants, right? And then we have psi j m max. There's no operator acting on the psi j m max anymore, so we could just cancel these things out, right? And then we are left with an equation that is h bar squared k squared is equal to h bar squared m max times m max plus 1, right? And you could do the same thing and determine the minimum value as well. For m minimum, you do using the same method that I did for m max, but the only thing that would change is instead of using psi j m minimum, you would use psi j m maximum, and the other equation for j squared, that was, you would change this, you change the positions. So in place of j minus, you would have j plus, and in place of j plus, you would have j minus in this one, right? And what that would mean is that you would have to switch positive sign over here, right, with a negative sign, right, to determine the minimum value. So I'm not going to do that all of this over again. You could do it yourself as an exercise. So what you would get is, at least let me write it down over here. So for m minimum, what you get is h bar squared k squared is equal to h bar squared m minimum times m minimum minus 1 this time, right? So this is what you get. Now I could draw this thing out for you, that you would have some minimum value, or the negative k over here, right? And you would have some positive k over here, right? This is the difference. And for some minimum minus k, you would have m minimum, and for plus k, you would have m maximum, right? And all the other states, for example, you would have over here, this would be m max minus 1, right? And it would keep going until you have some m, right? Some value of m, and then it would be m minimum minus 2, or I should have done it from here. So this is m minimum. You would have m minimum minus 1, then m minimum minus 2, and it would keep going, right? It would keep going until you have some m, right? And then you could have m plus 1, m plus 2, until you reach some m maximum, right? Okay, so for this then we could write down simply that m max multiplied by m maximum plus 1 is equal to m minimum, right? M minimum times m minimum minus 1, right? Now, if you look at this equation, we have to see that when is this equation satisfied. And well, if you look at it, it is immediate from this that it is satisfied when m maximum is equal to the negative of m minimum, right? So with this condition, and note that we have j squared is equal to h bar squared k squared, which is equal to h bar times j into j plus 1, right? Now what does this mean for you? This means that m is going to run from minus j to some plus j, right, in unit steps. So well, that means that we would have j is an integer if m equals 0 is included. It is included in the sequence of m, and j is equal to 1/2 times some integer if m equals 0 is not included in the sequence of m. Now, for all of this, to digest all of this, let's quickly look at an example, right? So say that you have some j, right, and it's equal to 2, right? So the quantum number j is 2. And what that means is that your mj would be, it is 2 times j plus 1. So if I were to substitute j equals 2, I would have 2 times 2 is 4 plus 1, 5, right? And so for that, then I can draw this spectrum as, for some j is equal to 2, it would split into, well, first we would have m equals 0, then it would split into m equals 1, then it would split into m equals 2, right? And we would have this splitting of m equals minus 1, and finally m equals minus 2. So it's going from minus j to plus j. So what that means is, then this is for m, right? So m would have values minus 2 because j is 2, right? So minus 2, minus 1, 0, 1, and 2. And that's what we see over here. So that's how it splits into different m, right? Okay, now let's quickly recall the ladder operators, right? The definition of ladder operators from L plus minus acting on the spherical harmonics y lm theta phi, right? We talked about the spherical harmonics in depth in well, not in depth, as a review, right, in the previous video on the part 1 of angular momentum review. Well, this thing is simply equal to some coefficients, right? So it would be s c plus minus lm times y theta phi, right? So this action of plus minus, we are absorbing it in these coefficients with this c plus minus. Now we could write these spherical harmonics, right, y lm theta and phi. We could represent them with just this in bracket notation as this ket l m, right? There is a comma in between, but I might be sometimes missing that out, so I might be writing this lm like this. It just means this thing, l comma m, right? So I hope you don't get confused. Well, from this now, our task over here is to figure out what this would be, right, in terms of course, L and M. And well, we had this orbital angular momentum, but now we are talking about total angular momentum. So wherever we have L, whether capital or small, we would replace that with J. So then what we have is J plus minus Jm is equal to C plus minus Jm and Jm plus minus 1, right? In fact, this thing, right, in a ket. Now we are going to derive C plus Jm, right? That's not M. Yeah, we are going to derive this constant, right? And then I'll directly write C minus Jm. You could also derive, of course, C minus Jm, right? And then again, I would leave that as an exercise for you to do. But of course, I will write down the value, right? Now, since Jm, right, these states, they are normalized, we can use this equation and write down that J plus on Jm is equal to C plus Jm and Jm plus 1, right? And then I'm going to take this thing on this equation, that is Jm J minus. So I'm going to operate on I'll just take this thing on this equation from the left hand side. So well, let's just not talk, let's actually go ahead and do that. So well, then that thing is Jm, right, J minus, which is this thing. Now I'll take it on this equation. So for the left hand side, I would have this J plus Jm, right, which is equal to, now I have to apply this thing on the right hand side as well. So Jm J minus, and we have C plus Jm Jm plus 1, right? Okay, so well, if you look at this now, what I can do over here is yeah, this thing actually becomes this right hand side. Yeah, actually this thing should be written as Jm J minus J plus Jm is equal to this square of jm cjm plus, right, and jm plus 1 and jm plus 1. Right. Now, yeah, a quick reminder would be is that recall that j square is j minus j plus jz plus h bar jz, right? Well, this implies that then I can write my j minus j plus from this equation, right? So I'm just moving terms here and there. So I could write j minus j plus as j squared minus jz and minus h bar jz, right? So if I have this, then this thing, right, as this thing is c plus jm, absolute value of this squared is equal to jm j squared, right? I'm putting this thing in here, right? So that is j squared minus jz minus h bar jz, right? Okay, actually 1 minute. We have a square on this jz, right? So it's like this. So we'd have a square on this. I'm sorry, I forgot this squared over here, right? Okay, so yeah, now we have this thing, and sorry, we don't have a square on this one. We have a squared on this one, right? And above here, it's correct, right? Okay, so this is what we have, and this is then acting on jm, right? Now from this we could simply act these operators one by one. So first we would have jm and this operator j squared on jm, right? Then minus this jm and this jz squared jm, and then again this minus, right? So minus jm h bar jz jm. Now again h bar is a constant over here, so we could throw it out. Well, let's see what this thing becomes, right? So j squared acting on jm would simply give you h bar squared times j into j plus 1, and this is just a constant and we could throw it out, so we would have h bar squared j into j plus 1, right? And then this state jm, and then when you act j squared on this state, it would also give you back the same state, so jm, right? And then likewise we would do for this rest. We would have this jm, actually let's see, jz squared acting on jm would give you m squared h bar squared. So jz squared just means it's acting 2 times. So once it will act on jm, it would give you m h bar, and other times it would act and it would again give you m h bar, and of course the same eigenfunction jm. And so that's why I could write this m squared h bar squared, and we have this jm, and it would give you back the same function, so we would have jm like this. Then we have this minus, we could already take this h bar outside, so we have this h bar, and then jz acting on jm, again it gives you m h bar, so it would be h bar squared m, right? And we would have this states Jm, and it would give you back the same state, so Jm. Now know that these states are normalized and they're orthonormal, so these would just go to 1, right? As because they're the same states, so they would just give you 1 if you take this inner product. Now with this, then I have my let's see, we have on the left hand side, we were doing this for C plus Jm whole squared is equal to h bar squared. We could factor h bar squared from these three terms outside, and we are left with j into j plus 1 minus m into m plus 1, right? And that's it. And we have, of course, these jm and jm, but they would all become positive 1. So finally, what we have for CJM plus is equal to, the absolute value of this is equal to the square root of all of this. Well, square root of h bar squared is just h bar. And we would have, now note that we are taking the absolute value of this. That's why I did not include negative h bar when I took the square root of this expression over here, right? And then I would have square root of j into j plus 1, right, minus m into m plus 1 from this expression, right? So that's my CJM, C plus JM. And likewise, if you do the same thing for CJM minus absolute value, you would end up with h bar square root j into j plus 1 minus m into m minus 1, right? So these are your two expressions for these coefficients C, J, M. And we can, well, finally generalize it to, well, say it's J plus minus is acting on Jm. It would give you h bar square root j into j plus 1, right, minus m into m. Well, for plus we had for CJM plus we had m plus 1, and for CJM minus we had m minus 1, right? So m plus minus 1, right? And we would get the states as j as it is and m plus minus 1. So the increment or the decrement is in m. And with this, then we have all the tools that we would need from angular momentum now. And so in the next lecture, I will talk about the central forces, right, where we will look at the Schrodinger's equation describing the motion of a particle with mass m in some potential v of r. And so from that we could talk about hydrogen atom, that is, it's a 1 electron atom. But of course we would be needing a lot of tools, and that's what we are actually developing right now. We would have to look at even the perturbation theory. So we will quickly revise perturbation theory as well in one of the lectures. So that's it for this angular momentum.